Okay, today we will make a compressor model in DWSIM. So before starting, I assume you already know the basics of DWSIM, so I will not spend time about the property package and very simple things. So I will just jump straight into it to save our time and to make a video short. I will do a centrifugal compressor or any compressor for a methane-ethane mixture. Gases composition normally is 90-10 or 80-20, so I will use 90-10 for the first case, and that we can change it later. Inlet pressure of 1 bar, outlet pressure let's assume is 20 bar, and flow rate I assume 8000 cubic meter per hour. I will use different approach with pressure targets, and I will also use the performance curves. I do not have the actual performance curves, so what I will do, I will just assume some values and then we can see how it will operate. And at the end of the video, I will briefly show how we can control the model from Excel. So let's jump into it. Start from new process model. Just keep it as it is. I'm using methane and ethane. Property package, I'm using Peng-Robinson. I need to double click it. And units, use whichever you like. I'm using C5 because temperature I need it in C, pressure in bar, mass flow rate, volume flow rate cubic meter per hour. It works for me. And but you can just change them also as per your needs. I'm not doing anything here. If I'm making a very complicated flow sheet, I put it as a no auto connected edit subjects, but for this it's fine because I'm only making a compressor, so it will auto connect it. But if you are making a complicated bigger process, then I would suggest you to turn it off. So first let's start with stream compound amounts. 0.5 is DWSIM equalize every component in the beginning, so you need to change it. I'm using 0.9, then enter. Here either you enter 0.1 or you just normalize it, or 0.9 and 0.1. Accept changes. Stream conditions 25. I was using 25 there, or temperature was not given, so 25 Celsius is fine. Pressure 1 bar is equal. Volume flow rate 8000 cubic meter per hour. And then you need to go to compressor and calculation type outlet pressure. Outlet pressure is shown as same, so you need to increase it to 20 bar. Adiabatic efficiency or isentropic efficiency, just keep it to 75%. And the model is already solved, and you see the power requirement is 772.53 kilowatt, and the temperature of outlet stream is 319 Celsius. You can also insert property table. Click it. I need stream 1 temperature, pressure, mass flow. Stream 2 temperature, pressure, volume flow, basically not mass flow. And E1 I need energy flow. So it shows stream 2 has a 319 degrees Celsius at a 75% adiabatic efficiency. If you increase the efficiency, temperature will go down. Let's say 85%, temperature is now to 90%. Now there is a concept of adiabatic efficiency or polytropic efficiency, whichever you want to use. I suggest you to look upon it. Like, what's the difference between adiabatic and polytropic efficiency? Briefly, adiabatic efficiency is isentropic compression, is reversible, and obviously it's adiabatic, and there are no heat losses from the compressor casing, causing the entropy to rise or change. But as you already know, isentropic or adiabatic compression is not reality. It's far away from reality. In reality, when gas is compressed, not all of the work done on the gas gets converted to a rise in pressure, because it has to have some thermal losses, friction losses, or even aerodynamic losses, and we quantify those losses as entropy. So uh, for this we need to use polytropic efficiencies. So if see whatever you want to use. So my rule of thumb is, if I'm only making a very small single stage compressor, I rely on adiabatic isentropic compression. But if I'm trying to make a realistic system with multiple compression, or compression ratio is very high, then I'm using polytropic efficiency. Did you remember when the adiabatic efficiency was 75%, the temperature was 319. So let's see the temperature. What would be temperature with similar polytropic efficiency? 339. So temperature was high, temperature was not low with polytropic efficiencies. So that's a simple concept. Okay, now back to the simulation. We use outlet pressure. If you can use, do you want to use pressure increase, you can also use pressure increase. So then you need to minimize it. For example, if you want 20 and inlet pressure is 1, then you use 19 something. Inlet pressure is not actually 1, it's 1.01325. So now it's 20 bar. Yep. Or if you want to use, you can say, if you have power required already, then you can just mention. For example, if I add more power, the pressure outlet will be more. Instead of 20, it should be something 22, 23. Oh no, it's 29. So with 1 megawatt it's almost 29. So 850, it was almost 20. You can also use energy stream. In energy stream, then you need to mention this power here. So go to the energy stream and click 1000, it will be 29 something, pressure will be 29. Yep. And or you can use compressor a non-head, or performance curves, or pressure ratio is also fine. So here you can use 20. So it will have outlet pressure over inlet pressure is the pressure ratio, and then you can change. So to model compressor is quite simple. Or you can have the performance curves also. In performance curves, so it's good to model if you have the performance data for your system, and then you need to edit performance curves. So you click on it, add new curve set. You can either import it, export it, or you can just use this. So flow rate, I'm using meter cube per hour. Head, I'm using meter, and flow rate again meter cube per hour, and efficiency in percent. So do you remember my compressor was around 8000 cubic meter per hour. Let's assume it's a designed case, so we can go 4000, 6000. These are part load operation, 8000, and we can just go above also a little bit, 12,000 let's say. With 40,000, let's assume I had a 4,000 cubic meter per hour. Let's assume I had a 40,000 with 6,000, 50,000, 8,000. You would say 60,000, and then head will reduce again with higher flow rate. Again 45,000 and 35,000. Let's assume it. And similarly 4,000, 6,000, 8,000, 10,000, 500, and 12,000. And efficiency will be, let's assume at lower load 68%, increase that to 70%, 78% with hard load, and 10,500 at 65% again, or 50%, and here use 75 that we are using originally. Yes, that's it, and then you run it. So because it's you would say here we are using flow rate of air 8,000. You see pressure is now 17 bar, and if you reduce it to 6,000, pressure will go down and the power will adjust accordingly. Let's say if we go a little bit higher, 10,000, so pressure is now again lower. So it's just dependent, it's just correlating our, you would say, performance curves, and also the efficiency is adjusting accordingly. So, and also if you just let's say if I'm using very low volumetric flow rate which is not given in performance curves, yep, it extrapolates it and gives us the outlet pressure and also the energy flow. We can also see the efficiency is now 60%. So that's how there are various ways you can just model it. Let's go back to the outlet pressure because I want to show you another thing. Pardon. Efficiency I'm using 75%. As how to control this flow sheet via spreadsheet, because it's easy. Now you are going with different things and changing everything, so it's easy there. Inlet temperature, inlet pressure, inlet volume, and outlet pressure, efficiency. So for example, inlet temperature you want 30 instead of 25. Outlet pressure you want 2 bar. Inlet volume you want 6,000. Outlet pressure you want 25 bar. Efficiency you want 80%. So how you can do it? Let's use this. Right click it. Now we need to import flowsheet object property. Use all edit objects. Object 1 is the stream. We want temperature in degrees Celsius. No, we need to export it, sorry. Export, because we need to send it back from here. It will give error, so just ignore it for the time being. Export again. Pressure in bar. It will again give error. We need to send the volume also. Volumetric flow rate in meter cube per hour. Again. Remove it, and we need to use the outlet pressure. Give export. Now compressor outlet pressure in bar, and you also want to export efficiency, adiabatic efficiency. We can only send adiabatic efficiency there, so that is fine. Okay, so now what you need to do it, here it gives error because value cannot be null, because now its value is null, so it has this is the unique ID for that object. Don't change it. So here you need to use B2. B2 is inlet temperature. So now you see it is exporting 30 Celsius, and here you need to use B3. It will use 2 bar, and here you need to use B4 for volume, and outlet pressure you need to use B6, and 25 bar, and efficiency is B7. Yes, and now what we are importing, we want to see a power required in kilowatt. Format cells, number 2 would be fine. This is in kilowatt. Yep, that's good for the time being. Let's go to the flow sheet to see. And spreadsheet again, now when you run it, you see it will it's already automated here. So let's assume I'm using 35 Celsius. Inlet pressure I'm using 3 bar. Outlet pressure I'm using 40 bar, and solve it. So you see temperature is now 35, inlet pressure is 3, volume is now 6000, and let's see if it changed the efficiency also. Okay, adiabatic, we need to go to the, it changed adiabatic efficiency to 80% also. But let's say instead of 80 we want to use 85. Outlet pressure instead of 40, 35. Run it again, 35, 85%, and the power requirement will change. So it's a very nice way to uh, use. Link your spreadsheet with your model, and then you can just change it accordingly. You will save a lot of time. I will do this also detail with other uh, models that I will simulate, but I think we should finish this simulation now.